single slit interference, and we want to prove a formula, and that formula is basically this thing. The intensity is I naught times this function where this f thing is sine x upon x. We are going to prove this formula, so we'll start from the basics. So first of all, we will just consider the phase difference between two rays from two different sources. So this whole plate, it's basically considered to be a lot of sources, in this case capital N sources, each of the same amplitude, and we define the amplitude and intensity at this midpoint because of all these sources to be A and I naught. Then you have some declarations that this distance is D, capital D. This distance is D by 2. So this complete plate thing, it is of length small d. This angle is theta. So the ray going from the center, the point O, to whatever point is on the screen, that ray has an angle theta with the horizontal. Since this plate is so small in comparison to the height of this point on the screen, we can assume that these two rays are like almost parallel, where of course you are assuming that this capital D distance is like very large. So with that assumption, you can do some angle chasing. So these are almost parallel, then this angle turns out to be theta, because if you draw this horizontal over here, this angle will be theta and this will be 90 minus theta, but then this thing, right, this thing with the horizontal, this angle is 90 degrees, so this angle should be theta in that case. So now that's nice. So using some trigonometry, we can say that this red length, it is x sine theta, and this red length is also the bar difference between these two rays. Why? Because if you consider this complete thing, right, this length of the shorter ray, that to be a radius, and you make an arc considering this as a center, then that arc will cut this thing at some point over here. So it will cut it almost perpendicular to this ray. And that's because these two are almost parallel, right? They are almost the same ray. So it has to cut with almost 90 degree. And that's why we can say that yes, this is also the part difference. So the part difference is x sine theta. Okay, so from that we can figure out what the phase difference should be. So the phase difference will be x sine theta times 2 pi by lambda, where lambda is the wavelength of whatever light is falling on the screen. So if wave from O creates the pressure variation at x, so in this case we are considering sound waves, I think. You can consider light waves as well, but let's just say that we are considering sound waves and lambda is the wavelength of that sound. Okay, so if wave from O creates the pressure variation at x as P equal to P naught sine omega t, then wave from A might be creating this thing. So it might be plus, it might be minus, we don't care about that, right? It all depends on what sign conventions you have. What is this? Is this thing like positive, negative? You can change that as per your will. So really we just look for the magnitude of the amplitude. Okay, then consider amplitude of interference at central maxima where theta is 0 and phi is 0 to be A. So when all of these sources have their pressure variation at this midpoint M applied at the same time, that interference that will create basically just the addition of all the amplitudes. So what we can say is that amplitude upon the number of sources, that will give us the amplitude of each source, of course at a distance of capital D, approximately capital D. So the interference of all of these sources for this point capital X, all right, so you have all these sources with almost the same distance capital D, and so they have almost the same amplitude, but their phases are different. So what will be the amplitude of the final interference at this point capital X? That's what we want to find. So we can say that the interference will basically give the pressure variation as this sum. So let's break this down. So it's a sum from I equal to negative n upon 2 to n upon 2. So this would be the last one of these, that would be the negative n by 2th source, and this would be the 0th source. I know this is very weird and unconventional. Why should we count from negative numbers? But I mean, if programmers can count from 0, we can as well count from negative numbers. Who cares? So it's from negative n by 2 to n by 2 of, so the amplitude of each of these small sources at a distance of capital D, that would be capital A upon n. Okay, and then you have this function. So that's with any sinusoidal wave, you have to put this function, and then there's this phase difference. So this phase difference is dependent on which point we are talking about, right? So the phase difference from the central source, of course. So this summation, as capital N approaches infinity, can be written as an integral. So this basically becomes this integral, which is not that hard to calculate. So doing all the calculation, it finally turns out to be this thing. This amplitude, it is in blue brackets, times sine omega t. So we finally found out what amplitude it should be. It's going to be a sine of whatever this thing is upon the same thing. What is this thing? Pi d sine theta upon lambda. Right. So first of all, we need to consider how this sine of x upon x function really behaves if we want to do anything with this. Because yeah, sine x upon x, it's a weird function. We have not seen a graph for that in, yeah, I don't think we have seen a graph for sine x upon x. We have seen graphs for sine x, for 1 upon x, for things like that, not for sine x upon x. So first of all, we'll try to graph that. So first we differentiate this thing, and that gives us f dash of x equal to this thing. Then we try to solve when is f dash of x equal to 0. So the values of this equation, that would be very close to like 3 pi by 2, negative 3 pi by 2, and also 5 pi by 2, negative 5 pi by 2, plus minus 7 pi by 2, so on. Right? Not exactly at those values, but very close to that, because this tan x, it goes like an asymptote over here. Yeah, it goes like this, and it mostly lies very close to this 3 pi by 2, x equal to 3 pi by 2 line. So wherever this line y equal to x will intersect with this blue curve, it will be very close to 3 pi by 2. So yeah, we know that the roots are going to be close to this 3 pi by 2 and negative 3 pi by 2 and plus minus 5 pi by 2 plus minus 7 pi by 2, so on. So at those points, we will have extremum values. So we can start graphing from there. Before that, we also need what will this function approach as x approaches 0. That is 1 in this case. This is a very classic limit. Everyone knows this, that this approaches 1. So finally, we can start actually graphing out this function. So first, it's 1. Then at pi, it will be 0 because sine pi is 0 and x is not 0, so it is definitely 0. And that means that first it's 1, then it goes to 0, and till here there's no extremum point reached, which means it is continuously decreasing for that to happen. And then it keeps on decreasing till it reaches 3 pi by 2, near which it will have an extremum value. So it will after that start increasing, and then it will increase till 5 pi by 2, and yeah, it keeps on happening, and it will basically become 0 at 2 pi because sine 2 pi is 0. So at n pi, this amplitude value, it just becomes 0. Well, I should not say amplitude, I should just say sine x upon x, because we have not yet got to that amplitude function yet. So at n pi, f of x becomes 0. Well, that's nice. And at odd multiples of pi by 2, or some odd multiples of pi by 2, this function reaches its minimum, local minimum or local maximum value. So that's for f of x. What about mod of f of x? Well, mod of f of x would have its minimum value as 0 because it's positive by default, and that would be at these integral values of pi by 2, and it would have the local maximum values at these odd multiples of pi by 2. Of course, excluding this pi by 2 and negative pi by 2, because yeah, those don't work. Right. So f of x is max locally near these values. At these values, f of x squared is also max, because really f of x squared is just mod of f of x squared. So if this guy is maximum, this guy is also maximum. Right, it's positive anyway, so we can definitely do that. So at x equal to some integral multiple of pi, it's minimum 0 basically. And now we come back to our amplitude function. So it was a sine of pi d sine theta upon pi d sine theta upon lambda, which is basically a f of pi d sine theta upon lambda, where f is sine x upon x, the function that we just considered. Well, that's good, but let's talk about intensity instead of amplitude. So you know that intensity is proportional to amplitude squared. So using that, we can say that I at the point x is I naught, which is at the point m, times this function squared. Okay, so we just saw that f of x squared, this is minimum when the inside value, that x thing, is some integral multiple of pi. So minimum intensity is when this thing pi d sine theta upon lambda is some integral multiple of pi, and solving that we just get d sine theta equal to n lambda, where n is some integer. And maximum intensity would be when x is near to these points, 0, plus minus 3 pi by 2, and so on. So solving that, we get d sine theta is approximately 0 plus minus 3 lambda by 2 plus minus 5 lambda by 2 for the maximum intensity to happen. So yeah, that was the whole thing. So now we know how single slit interference kind of works. Not exactly, but well, at least these approximate roots work practically. So that's good. And I'll see you guys in the next video.